Alright guys, this is lesson 1 of differential equations. Yeah. Okay, first I'd like to start off by asking you to find the derivatives of f of x times g of x.
Wouldn't you just use the product rule?
Yeah. So this is the 0th derivative, right? The next derivative, or the first derivative, would you'd use the product rule, which would be f prime of x, g of x, plus f of x times g prime of x. And then this is the 0 derivative. This is the first. Now the second. Here we do the product rule twice for each of these two parts of the function. So for the first part, it would be f double prime of x, g of x, plus f prime of x, g prime of x. And then for here, it would be f prime of x, g prime of x, plus f of x times g double prime of x. The second derivative is that, and it can be simplified further into f double prime of x times g of x plus 2, because we have 2 of the same term, times f prime of x, g prime of x, and then the last term, f of x times g double prime of x. And then the next derivative, which is third, you'll just do the product rule again for all of those. And then you end up with f triple prime of x, g of x, plus f double prime of x, g prime of x. Plus 2f double prime of x, g prime of x, plus 2f single prime of x times g double prime of x, plus f of x prime g double prime of x, plus f double prime, or f of x times g triple prime of x. And this can be condensed into this f triple prime of x, g of x, plus this term and that term, which is 3f double prime of x, g prime of x, and then these two terms, 3f prime of x, g double prime of x, and then this last term, f of x, g triple prime of x. And if you look at each of the coefficients in this progression, and we label them as such.
Oh, is that Pascal's?
Yep, that's Pascal's. So that would just be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And you can just assume that it would go on forever, which it will. Alright, that was just something fun. I thought it was fun at least, but
Would you use that for?
if you had like f of g to the 56, maybe.
Oh. I'd be a really big triangle though.
the actual differential equations part. Okay, Josh, do you know what a differential equation is?
Is it an equation that can be derived? It can go to the.
Well, any equation can be derived, for the most part. So a differential equation is y equal x a differential equation?
Yes, that would be a differential equation. Because wouldn't you have?
No, it's not.
Or it's not.
Because y isn't being derived. It's just a regular equation. How about this? Is y prime, y double prime plus 3y prime plus y equals, I don't know, sine of e to the x. Is that a differential equation? Yes, it is, because you have different derivatives of y. What about this one? Y double prime is equal to the e to the 3x. Is that a differential equation, Josh? No, it's not. A differential equation must have one of its derivatives and the original function itself. Or else this could just be written as like, let's say y double prime equals v, and then you just say v equals 9 e to the 3x, which is not a differential equation. So, yeah, another differential equation could just be like y double prime is equal to y. That's a differential equation. It doesn't really need x per se, just y and its derivative, or at least one of its derivatives. Let's try some simple differential equations. If you had y prime is equal to 2y, can you think of a function that would fit that? Or its derivative is equal to twice the original function? Hints? Chain rule, where you have to chain on 2.
Oh, is it what x squared? Or
Not x squared.
not exactly.
First, what's a function whose derivative equals itself?
E.
E. So y is equal to e to the x. But that doesn't solve this differential equation.
You would have
To
to
get
have
this 2, we need a chain on the 2.
Oh, you'd have to have it like e to the 2x.
Yep, e to the 2x. Because the derivative of e to the 2x is 2 times e to the 2x, which is twice the original function. So we could generalize this by saying that y prime is equal to k e to the x, or my mistake. Let's say ay. We can generalize the solution to this by saying that y is equal to e to the ax. Let's try something a bit enticing. Y double prime plus 4 y prime plus 5 y is equal to 0. I'm not really expecting you to understand this, but if you do, that's amazing. Not gonna lie. Also, when you have a 0, that is the same as saying it's a non-homogeneous differential equation. So if you ever hear non-homogeneous, that just means that equals 0, and there's no x's. So taking what we know here, we could apply it to these equations too. So if, let's say we have y equals e to the ax as a solution, then we could say that y prime is equal to a to the e to the ax, and that y double prime is equal to
A squared.
Yep, a squared e to the ax. So we plug it in back here, all these three forms of y. We could write it as y double prime a squared. I'm gonna write r squared because that's generally how it's written. So r squared, let's just say r equals a. So r equals a, so it's r squared e to the ax, e to the rx, plus 4r e to the rx, plus 5 e to the rx equals 0. Do you know what you could do after this?
Wouldn't you factor out all the e to the rx?
Yep. And then what do you do after that?
Wait, so do all the e's cancel out? So it's just r squared? It's a, oh, isn't that a quadratic?
Yep,
So then,
that's exactly right.
so then that would just be r plus, oh, okay. Yeah, r plus 4 times,
I'm sorry, that's my mistake.
oh, okay, that makes a little more sense. Yeah, r plus 5 minus,
Yeah, that needs I. So r plus 5 times r minus 1 equals 0. So you know that r equals -5 and 1. Do you know what that means? R is just some constants. But what the context of this constant is y equals a to the rx. So you can say that y is equal to e to the -5x, and y is also equal to e to the x. And those are solutions to this differential equation.
so just specific to that
Yep.
non-homogeneous diffie cube.
Yep. And these are both solutions, right? But there's this principle called the superposition principle that states that if you have two solutions or more to a differential equation, any combination, any linear combination of these two solutions is also a solution. So you could write a general solution of y is equal to k1, which is some constant, e to the -5x plus k2 e to the x. And that is your solution.
And how exactly does that work again? How's that able to work?
This part? Why don't we test it out and see if it does work? So we have y equals k1 e to the -5x plus k2 e to the x. So that must be that y prime and y double prime are equal to -5 and 25 k1 e to the -5x plus k2e to the x. And if you plug those back into this equation, you'd be left with 25 k1 e to the negative 5x plus k2 e to the x plus 4 times y prime, which is negative 5 k1 e to the negative 5x plus k2 e to the x, and then the last term minus 5 times y, which is k1 e to the negative 5x plus k2 e to the x. So if we isolated all the k1 to the k1 times e to the negative 5x's, you'd have k1 e to the negative 5x times 25 minus 20 minus 5 plus k2 e to the x times 1 plus 4 minus 5.
So the k2ex, does that get all canceled out?
k1 e to the negative 5. Yep, it all cancels out.
Oh, ends up equaling 0.
Yeah, and we had originally this equals 0. So 0 plus 0 equals 0. What's 0 plus 0?
0.
0. Are you sure? You all get graphic calculator check or something?
I kind of lost my graphing calculator.
Alright. I'm gonna assume it's 0. 0 equals 0.
We don't have to prove that it equals 0, right?
You gotta take the limit as x equals, as x approaches infinity to solve that's 0. Yeah. And so this is how to basically prove that any solution is a solution to a differential equation. It's basically a check step. But you're gonna find that this comes in handy a lot because it reassures you that that's the solution.
Wait, so what makes a differential equation non-homogeneous?
Non-homogeneous just means that the sum of the y's and the forms of y equals 0. If this was equals sine of x, or equals ln of inverse secants of, I don't know, e to the 5 to the x to the cosine power or something like that. Something crazy. That's homogeneous. Oh, my bad. That is actually homogeneous.
Oh, so then
Yeah,
non-homogeneous.
homogenized milk. Yep, exactly the same.
Oh yeah, makes sense.
Yeah. And I'm sure you've noticed, but all of this was basically algebra.
Yeah.
Yeah, 90% of differential equations is algebra. There's 10% of differentiating, but that's about it.
Yeah, there's a lot of substitution.
Yeah, a lot more than this, way more. Okay, let's try another example. 2y double prime plus 5y plus 2y equals 0. So you know you could just substitute y equals e to the rx. And it's generally just easiest to just replace like y double prime with like r squared and then y prime with r and then y with 1. Just because it's kind of simple.
Yeah.
It's kind of easy to relate this to that. Just remember that y doesn't equal r, y prime equals r. Because that tricks some people. So then you solve this, and then you get, do you know how to factor this?
No, I don't.
2r something times r something. You would do plus 2 and then plus 1. Do you see how that's the same thing as that?
Yeah.
2r, 2r squared. 1, 2, 2. 1r, 2 times 2r is 4r plus 1r, that's 5r. Yeah. And then the solutions to this are -2, -1/2. So y is equal to k1 e to the -2x plus k2 e to the -1/2x. And those are your solutions. If you want, I could check it, but Okay. This is, I guess, the last part of discussion for today. I guess this is the short lesson, or shorter than last time at least. Do you remember what a discriminant is? Not determinants, discriminants.
Discriminants? No.
Yeah. No? If you have a parabola, right? Looks kind of like that. The discriminants, or this parabola is in the form y is equal to ax squared plus bx, and then you know the gist.
Yeah.
The discriminants is, the quadratic formula is y equals -b plus or minus the square root of b squared minus 4ac all over 2a.
Oh, you should probably see.
Oh, the c, yep, you're right. The discriminant is this part.
Oh.
So it's just the square root of b squared minus 4ac. And this determines how many solutions you have. If it's negative, then you have 0. If it's positive, you have 2. And if it's 0, then you have 1. So let's say we have a case where this equals 0. Let's say we have some example. Let's say y double prime plus let's see, plus 4r, not r, my bad, plus 4y single prime plus 4 equals 0, or 4y. What's the first step, Josh?
Oh, you plug them in, right?
Yeah.
So you have your you'd have your r squared.
Mm-hmm. R squared plus 4 times what?
4r and then plus 4.
Yep. And how do you factor this?
You could factor that using r plus 2 times r plus 2, right?
Yep. So r plus 2 squared.
Yeah.
And so you have the solutions. Y is equal to e to the -2x, and then, wait a minute. You have 2 of the same solution.
But then, could you use the superposition thing and add them up?
You could. But
yeah, it's still
the
K1
thing
and
is,
K2.
with these differential equations, the highest degree is how many solutions you have.
Mm.
So if you had like y to the third power, or not y to the third power, y triple prime plus this, you'd have 3 solutions. So why don't we try, let's try times x. What's the derivative of k2 e to the negative 2x times x?
You have to do the product rule.
Yeah. So it'd be k2 times negative 2 e to the negative 2x x plus e to the negative 2x. And then the second derivative, or that was the first derivative, and now the second derivative. That is k2, and then do the product rule. And then that's 4e to the negative 2x x minus 2e to the negative 2x plus, minus 2e to the negative 2x. And so if you plug these back up into here, we are left with y double prime, which is k2 4e to the negative 2x x minus 2e to the negative 2x minus 2e to the negative 2x plus 4 times the first derivative, which is negative 2e to the negative 2x plus e to the negative 2x, and then plus the first one times 4, that's 4k2 times k, or not k, times e to the negative 2x. Oh, and then times x. And then this has an x too. And so if you add these all up, let's see. We can just cancel out all the k2s and just like have that distributed, I suppose. Let's group all the x's. You have 4e to the negative 2xx, and then 4 times negative 2e to the 2xx, and then 4 times e to the negative 2xx. That is, I'll just factor out the e to the negative 2xx again. And then you just do the coefficients. 4 and then plus 4 times negative 2 minus 8, and then plus 4. And then the e to the negative 2x, all of those are negative 2, negative 2, 1 times 4, and then 1 times 4. Oh, I'm sorry, that's not actually, that has an x, so it doesn't count. So you just have negative 2, and 4. So you have minus 2, and then plus 4. And that is supposed to equal 0. And you can probably tell both of these are 0. So then it's k2 times 0 plus 0. What's 0 plus 0?
0.
Yeah. So it's 0, k2, 0, and that is equal to 0. So we have just shown that by multiplying x to a repeated root, you get another differential equation. So the overall solution to this differential equation is y is equal to k1 e to the negative 2x plus k2x times e to the negative 2x.
What same thing to k1.
If you added an x.
Yeah, if you just multiplied by the x, would that still be possible? Or
Well, they're the same thing now, so you just combine them. And then you don't have to add another x. But you can't just add as many x's as you want.
Yeah.
Because that would just be like, you know.
but like, could both of them have the x multiplied to it?
Well, this is always a solution though. This gives you one of the solutions. So there's no point in actually like getting rid of one of these solutions by like, I guess, violating it by adding an x, because then you're just eliminating the solution that is the solution. So you can't just say that's not a solution by adding that x.
Oh.
That's like saying like, if you had, I don't know, r plus 2 and then r minus 1. So r equals -2 and 1. You can't just hide the 1. The 1's always there. You can't just, get rid of it.
I mean, like, my question is that, like, you know how you just did a whole thing by multiplying the k2e to the -2x by x?
Yeah.
So if you did that, but instead to the k1, would it still be the same results?
So if you instead did this?
Yeah.
Yeah, because k1 and k2 are just arbitrary constants. So, I mean, in a sense, you could just do k2 and then k1. And then look, you have the same thing that we started with.
Oh, but does it have to be like that?
At least one of these has to be x.
It can't be both.
Because you have to have two solutions.
What if both of them had an x?
If both of them had x's,
Yeah.
then that would just mean that the k1 and the k2 cancel or combine, because they're just arbitrary constants. As of now, they just represent anything. So this could just be simplified as k1 plus k2 times x e to the -2x. But because k1 and k2 are just constants, let's say that's k3 now.
Oh.
E to the -2x.
So if they're just constants, it's just gonna equal a constant.
Yeah.
Okay, but I guess it would still be a viable solution. By
It wouldn't be a complete solution.
Would be a
because you're
complete
still missing this part.
Oh, so could it be something like y could equal k1 times e to the -2x plus k1 times e to the -2x times x, and then the same thing plus whatever that
Plus.
is, but with k2? Or
Well, I mean, k1 and k2 are just arbitrary constants. Like, we name anything as just.
Oh yeah. Oh, okay, that makes sense now. It makes sense. Okay.
So in reality, like the actual like pure, I guess, solutions that you found or solved for are just e to the -2x plus x times e to the -2x.
Oh, I
The
see.
k's are just added for completeness to make sure that you grab every single one of the solutions as possible.
Oh, okay, that makes sense.
The k's can actually be thought of as
Is it kind of like the
a
C's
side
in-
effect of
in-
the, what was it called? The superposition principle, which states that if you have like y equals e to the x, that's a solution.
So those k1s and k2s, is that kind of like the plus c and for like indefinite integrals, sort of?
Yeah, k's or the c's.
They're
Although
kind of
C's
treated
come
the
back.
same way.
The c's come back from cap BC to here.
Mhm.
But then c's and k's are basically the same thing. It's just convention to write k's when you're dealing with things.
Mm.
So if you go back to the superposition principle, you know that if y is equal to x squared, if that's a solution, then that means that itself is a solution as well, right?
Yeah.
But if that's a solution, and that is also another solution, then any combination of those two must also be a solution. So if you have y equals x, or y equals e to the x, and y equals e to the x, then y equals e to the x plus e to the x is equal to 2e to the x must also be a solution. And that could go forward like so on. Like y equals, I don't know, like 6, 7, 8, 9, 9, 9, dot, 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 e to the x. And that's still a solution. Because you're just adding more and more e to the x. You're adding more and more solutions.
Mm.
So you could just simplify this by saying, that y is equal to k1 times e to the x because the K1 is vague, and because of its vagueness and ambiguity, it covers a broad range of numbers.
So is adding that x to one of the components of y,
Yeah.
is that adding like another possibility or something? Because
Essentially, yeah.
because for that homogeneous differential equation, it goes until the second derivative, so that's the second possibility, sort
Yeah.
of, right?
Yeah, essentially, yeah.
So then if you had, okay, so I guess the question is, if it went to the third derivative, would the third solution kind of be like
X squared.
x squared?
You just throw in an X squared.
Oh, okay, because
Yeah.
that's another possibility.
Mm-hmm.
Oh, okay, I think I see where this is going now. Okay.